we will formally introduce scalar and vector quantities. Yesterday was the first class, so I just went about more like a oral discussion. Scalar quantities or scalars, quantities that have only magnitude and no direction associated with them. They are called scalar quantities. Example, distance, speed, temperature, density, volume, electric current, and so on. Then what are vector quantities? Quantities that have magnitude, direction, and follow vector laws of addition. This is important. Only those kind of quantities are called vector. And yesterday we looked at a few examples: displacement, velocity, acceleration, force, momentum. All these are vector. Okay. And vector quantities, you will have to handle them with care. You can't be negligent while handling vector quantities. Apart from that diagram, I mean this image, apart from this image, write down the rest of it. It will be useful. And once you have finished writing, use those emote icons, either a thumbs up symbol or a hand raise symbol. And once you finish writing it, please let me. Okay, Ayush has finished writing it. We'll just wait for a few minutes for others also to finish, and then we. Okay. Nevin and Prithviraj, did you also finish writing it? Done. Okay. Asma, did you finish writing it? Right. Okay. So now, yesterday, we did discuss about all this graphical representation of vectors and all that. Graphically, a vector is represented by a directed line segment. an arrow. We learned about that yesterday. The length of an arrow is an indication of magnitude of the vector. In many books and many teachers also, they just end up saying that the length of the arrow is the magnitude of the vector. That is kind of not completely correct, because a length can only be, for example, this length exactly is roughly around 4 centimeters, right? So can I use this to represent 10 newtons? Is this number equal to 10? No. Is a length same as Newton? No. Therefore, it should be very clear, carefully mentioned that the length of the arrow is an indication of magnitude. It means not exactly equal to magnitude, but it's an indication of magnitude of the vector. Okay. And the direction of the arrowhead is in the direction of the vector itself. Here are various examples for this. Initial velocity of a body which is thrown up with a velocity of 20 meters per second. Final velocity of a body if it is coming down with a velocity of 40 meters per second. Acceleration is always in the downward direction. Value is 9.8. This indicates a force applied in the right-hand side direction, and the value of the force is 20 newtons. Like that, there are so many examples. Write down these 3 lines and draw any 2 out of these, your choice. Or you can write any one of your choice. Just by getting the idea from here, you can draw a vector pertaining to a quantity completely upon your choice. A few people are yet to switch on the cameras. I really like if the students have their cameras on. If the background is a problem, then go to video settings, select blur background so that the background will be blurred. Just like you can see in case of Nevin, right? He has got the background blurred. So even if anyone is moving in the background, it doesn't matter to us. But otherwise, keep that video on. Finished writing the 3 sentences and drawing any 2 examples of your choice? Okay. So now, let us go to the next slide. Shall I move on to the next one? I'm just waiting for others also to write. And remember, all that we are learning under vectors should not be forgotten. It should not be treated like, this is from the first chapter. So we learn about vectors. We learn a few definitions and all that. We get our 2 marks or 4 marks in the weekend exam or in the board exam. And after that, we promptly forget about it. It should not be like that. It should be actively used from the first chapter itself. Motion in a straight line, motion in a plane, laws of motion, work energy power, gravitation chapter, rotatory motion chapter. All these chapters extensively use vectors. Without vectors, you don't even know where the body is going. You don't even know where the force is being applied. So you must learn that this is a tool, not just a 4 marks answer or a 2 marks answer so that you get away with it. It should not be treated like that. Okay, so we go to the next one. Textual representation of vectors. Yesterday, I told you there are 2 ways of representing vectors. One is with a bar over the symbol indicating the vector quantity, and the other one is writing the vector in a bold face. Here it is. Examples. Displacement. In the textbooks, you will find this kind of a notation, but when we write it in the notebooks, we use this notation. because writing S like this and keep on darkening it like this is a very tedious task, right? On the contrary, just putting S with a bar is much more easy. So all these right-hand sides, they are handwritten, and this is printed. In print, we use this. You need not write all these sentences. No one will ask you this. Just write down textual representation of vectors and write any one example out of this. That's it. You don't have to write those sentences. You must just understand how to write vectors in equations. That will be sufficient. Okay, and then before we proceed, let me give you a small piece of advice. That is one habit that I have. I keep sharing a few good things with my students. Whether they follow, whether they don't follow is entirely up to them. But I keep doing that. Buddha ho gaya. I'm growing old, so I'll keep giving these kind of sermons, right? May I assume that all of you are familiar with video games? I'm not saying addicted to. I'm not even using that. Familiar that there is something called as video games. Even if you don't play, you might have seen your friends, your classmates getting very busy with video games and all that. At least you know that there are something called as video games, right? In mobiles, laptops and all that. Those who are interested in video games or those who have seen your friends playing video games, just try to recall, have you seen your friends playing video games while eating a packet of chips, while listening to music, and while talking to another person, but still getting busy with the video games? Honestly, think for yourself. Have you ever seen this happen? I have personally never seen this happen. Especially when a person is playing video games, he or she will be totally immersed in it. Both the hands will be busy with the video game. I mean, you even shout out their name, they won't be able to listen to that, right? So, so my doubt is, while playing video games, when a person can be so, highly concentrating, not allowing any kinds of distraction, then how is it possible that only while studying, one has a packet of chips next to him, then there'll be headphones, some music will be going on in those headphones, then some mobile chatting will be going on, simultaneously with your friends, and at the same time, studies will be. Is that even possible? Think about it. Right? So at least next time, give as much dedication to studies as a child would for their video games. If at all you have observed that, right? Because while playing video games, you don't allow yourself any distraction. Then why should there be a distraction during studies? Think about it and it will be useful for you later. Okay, so let us come back to this. Types of vectors. Yesterday, I did not touch upon that. We directly went to addition of vectors. But then when we are studying about vectors, it is worthwhile to know about types of vectors. Here, first one is a unit vector. A vector of unit magnitude is called as a unit vector. Now, what is meant by unit magnitude? I hope everyone is familiar with this term. What is meant by saying unit magnitude? Unit magnitude means magnitude should be 1. Like earlier in the examples, I have shown you a force of 20 newtons. Is 20 equal to 1? No. Then you can't call it as a unit vector. Right? Unit vector essentially means a vector whose magnitude is 1. Only that is called as a unit vector. And since unit vectors are special, you indicate it with a cap on the symbol. Here are the examples. Suppose you want to say that there is a unit vector in the right-hand side direction. A unit vector along positive x-axis or towards right-hand side direction is indicated with a I cap, right? A unit vector in the upward direction is indicated with a j cap. You see along the y-axis, j cap. A unit vector along z-axis is indicated with a k cap. And as I say this, I already see some confused faces. That is the reason why I want the video cameras. Because from the faces, I can figure out that, yes, something has gone out. You are not able to understand that. I'll tell you. Suppose there is a ground. Okay, let me take a straight line and draw. Suppose there is a ground and there is a person running on the ground. Don't ask me why he is running. That's it. He just felt like running and he's running, right? And he's running towards right hand side with a speed of 20. Oh my God. Is it possible for a person to run at 20 meters per second? He'll be dead. Okay, so let us give him a fair deal. 10 meters per second. It means within 1 second, he has to cover 10 meters. The typical length of a hall in a reasonably sized house is about 7 meters, 8 meters. A person has to cover that and cross that within 1 second. Is that possible? It is actually possible. There is a gentleman called know this name? Usain Bolt, world's fastest runner. He covers more than 10 meters in 1 second because world record is 9 point something seconds. It's not more than 10. So there are people who run roughly 10 meters a second. So let us say our hero is very powerful, this fellow here, and he's running at 10 meters per second towards right hand side direction. Now, if you want to convey this information in the language of vectors, how would you do that? You would say that the velocity of the person, which is a vector quantity, is 10 meters per second in the right hand side direction. Notice what I said and notice what I wrote. I'll do that once again. See, velocity of this person is 10 meters per second in the right hand side direction. I said such a big part of a statement, in the right hand side direction. Did I write all that on the screen? No. So when I write it in this particular format, what does this indicate? This indicates magnitude. And what does this indicate? This indicates a specific direction. This I cap that I wrote, is it changing the value of 10 here? No. The number 10, can it give me the direction? No. So it is written in two parts. One is a 10, one is a I cap, and both parts have their own importance. 10 indicates how fast he is running. I cap indicates in which direction he is. So isn't I cap telling us only about the direction? That's it. If the person slows down, I can say that the final velocity of the person is 6 meters per second in the right hand side direction. This has changed, but did this one change? It is still indicating right hand side direction, right? Therefore, such vectors whose job is only to indicate the direction, they are called unit vectors. If you want to indicate a direction in the right hand side, use I cap. If you want to indicate a direction in the upward direction, use J cap. If you want to indicate a direction coming towards you out of the screen, that is called as K cap. Okay. Now using this notation, can anyone tell me that if a body is projected vertically up with a velocity of 40 meters per second, how do we write it?
Or J cap.
Q bar is equal to 40 in the upward direction. Notice that I'm saying in the upward direction, but I'm not writing such a lengthy phrase. I'm just putting a J cap. Right? Acceleration due to gravity is 9.8 meters per second square in the downward direction. How do we write all that? Acceleration due to gravity is 9.8 in the downward direction. Whenever it is like this, we need not be so specific. Another casual way of writing this is bringing the minus up front here, and we just write 9.8 J cap. The moment it is like this, you should clearly understand this minus is not because of 9.8. Minus is because of J cap in the downward direction. So in this case, isn't this indicating the direction? Isn't this indicating the direction? These kind of special vectors which indicate only the direction, they are called unit vectors. Now is the idea clear a little bit? Right? And as and when we use it much more frequently, the idea will be imbibed in you. You will start internalizing the idea. Then position vector. Very simple. A vector drawn from the origin to the instantaneous position of the body is called position vector. So whenever we draw an x-axis and a y-axis, suppose we draw an x-axis We draw a y-axis, and suppose there is a body here. Like suppose there is a potato here or something. You want to indicate the position of that potato. So what you do is, from the origin, you draw a vector to the body. This vector, which indicates the position of the body, is called position vector, and it is generally denoted as R bar. Right here, this is the printed format. Therefore, I have used a bold-faced letter. If it is a handwritten one, then you say R with a bar. Okay, but then this is very important. The vector has to be drawn. Oh God, there is a spelling mistake here in the PPT that I made. F-R-O-M. In these tools, I'll have to keep searching for that. F-R-O-M. Drawn from the origin to the instantaneous position of the body. You should not change the sequence and end up drawing it from the body to the origin. That should never ever be done. Always from the origin to the body only. That is called as a position vector. Then, next one is a null vector. Null vector is kind of a strange vector. A vector which has zero magnitude and unspecified direction. That is called as a null vector. Doesn't that seem a bit, unsatisfying? A vector doesn't have a magnitude. If it doesn't have a magnitude, it cannot have a direction also. Then it looks like there is nothing. Then why do we even call it as a null vector? We could have just called it as zero. You know why we call it as a null vector? To be very precise. The reason is, if there is a force of 10 newtons in the right hand side direction, F1, this is added to a force of 10 newtons in the left hand side direction. When you add both of them, F bar will be F1 bar plus F2 bar. When you add 10 to minus 10, what do you get? You'll get a 0. If I write just a 0, you know why it is wrong? How can a vector quantity be equal to a scalar? That is wrong. Because the 0 was obtained after subtraction of two vectors. Therefore, in order to be very specific, we put a 0 bar. You may still not be satisfied by it. You'll say, sir, what is this? It is just very clear that these are forces being subtracted. So why be so specific? Physics people are unnecessarily grumpy. They are very unnecessarily orthodox. Why are we doing all this? Today, it will seem like that. Later on, after your 11th class, 12th class is over, once you join BTech and all that, believe me, you will be doing derivations and problems that run into 3.5 pages. Easily. Right? Brace yourself up for that. You will be doing problems which will run into 3.5 pages easily. Then suppose your equation 5 turns out to be 0. And then you continue, and equation 16 is your answer, for example. Then if equation 5 gives you 0, you must have a track of, or you must keep a track of whether you got a 0 because of subtraction of two temperatures or because of subtraction of two velocities. Temperature 0 is the scalar quantity, velocity 0 is a vector. And so you want to keep track of those kind of things. And for a technical completeness, it means when you're subtracting vectors, even if it is a 0, it should be given that due importance and called as a vector. Therefore, we very clearly define a null vector. Okay? And then, these details you can write it later. Unit vector, position vector, null vector, you can write it later on. And this is there in my website also. Later on, you can copy it down or any standard book will. And since it's only a demo class as of now, that's okay. Whatever is the most important, I'll ask you. Equal vectors. Equal vectors, again, the definition could be very easy for you to understand. Two vectors, or think of any vector. What are the two qualities that a vector has? One is a magnitude, one is a direction. Isn't it? So when do you say that two vectors are equal? Naturally, when both these qualities match, you call them as equal vectors. That's it, as simple as that. Two vectors are said to be equal if they have same magnitude and same direction. Then you say that the vectors are equal. Fair enough? Then comes the next one, parallel vectors. Here, you don't say that two vectors are said to be parallel if they are parallel to each other. That is a nonsense kind of a definition. The vectors are parallel, therefore they are parallel to each other. What new did we say? Nothing, right? Therefore, we don't say it that way. First of all, you think of a reference line. Suppose you have some reference line, like a horizontal ground or something. Then, if there is a vector A that is parallel to this line, and there is a vector B that is also parallel to the line, then A and B are said to be parallel to each other. That is what this definition means. Read that carefully, you will understand. Two vectors are said to be parallel to each other if they are parallel to the same reference line. Is that clear now? Now, suppose I draw another vector. Is this vector C bar parallel to A bar? Can anyone answer that? Is this vector C bar parallel to A bar?
Yes.
Yes, right? The reason is because what did the definition say? A bar is parallel to this line. C bar is also parallel to this line. But you might protest saying that, but sir, this is in opposite direction. Is there any mention of direction anywhere here? It should just be parallel to the given reference line. That's it. So is A bar parallel to B bar? Yes. Is B bar parallel to C bar? Yes. Should they be of same magnitude? Not required. Should they be in the same direction? Not required. Right? They just have to be parallel to the given reference line. That's it. Then, what are like vectors? Two parallel vectors are said to be like if they are along the same direction, and unlike vectors. Two parallel vectors are said to be unlike if they are in opposite directions. Now, let us look at an example of all this. Suppose this is the reference line, and I'll draw a few vectors. This is A, this is B, and this one is C, this is D, this is E. Suppose you have so many vectors. This is A bar, this is B bar, this is C bar, D bar, and E bar. Out of all these vectors, which vectors are parallel to each other? Which vectors are parallel to
All are parallel to each other.
are parallel to each other. Got it? Right. Which vectors are equal? Which vectors are equal?
B bar and C bar.
B bar and C bar are equal. Which vectors are unlike vectors? Pick any one pair of unlike vectors or two pairs of unlike vectors. A and
A bar and E bar. E.
Right. A bar and E bar, because A bar is towards right hand side, E bar is towards left hand side. Similarly, you can say B bar and D bar, and C bar and D bar, C bar and E bar, any two vectors in the opposite directions. They are unlike vectors. Like vectors, all the three vectors that I have drawn above the line, they are like vectors. The two vectors that I have drawn below the line, they are also like vectors. Now, is this idea clear? Right. Should parallel vectors be like vectors? Not necessary. Should parallel vectors be unlike vectors? Not necessary. Should like vectors be parallel vectors? Yes. Should unlike vectors be parallel vectors? Yes. That is very important. Unlike vectors should also be parallel. A is unlike E, but still both of them are parallel to this reference. Okay. Then, now we come to the next point, that is for the types of vectors, negative of a vector. Negative of a vector is also an easy concept to understand. If you have a vector like this, a vector drawn of same length but in the opposite direction is called as a negative of a vector. So if you want to call this as A bar, this one same magnitude but exactly the opposite direction, this is minus. Fair enough, right? These kind of definitions are easy to understand. There's not much of a difficulty in this. Negative of a vector. There is nothing called as a negative of a direction. Therefore, we just say negative of a vector, right? If you want to speak in terms of direction, then you say opposite direction. That's it. Don't attach the term negative to a direction. There is no negative direction, right? Then, vector addition, graphical methods. Yesterday, we looked at parallelogram law of addition of vectors. But today, we will first look at triangle law, then go to polygon law, then come to parallel. Triangle law of addition of vectors. Just read this statement to yourself. You don't have to read it out loud. Just quietly read it and see if you have understood anything. Right? Looks like a very lengthy, complicated statement, isn't it? Isn't it? Is it looking very simple to understand? Those of you who find this to be very simple to understand, like you have just read it once and you have understood it completely, just raise your hand. But then you have to be honest. It is not like you have already known triangle law, therefore you find this easy. Not that. Those who are reading it for the first time and you have read it and you have fully understood it, then raise your hand. Right? So it is kind of troublesome, isn't it? A very lengthy statement. God knows what this statement means. Now let us try to analyze this. If two vectors represent two sides of a triangle, it means we have to first of all take a triangle. So let us do that. First of all, we need two vectors. Let us say this is one vector, this is one vector. These two vectors, now let me call this as A bar and let us call this as B bar. Now this A bar and B bar, the way you see it now on the screen, are they forming two sides of a triangle? No. So we have to make them look like two sides of a triangle. So I'll move this A a little bit here and I'll move this B a little bit here. Notice where I'm joining B. I'm joining the tail of B to the head of A. Is that clear? I have joined the tail of B to the head of A. That is what I have done. So whenever you are joining tail to head, it is called as taking it in an order. Taking it in an order means joining head to tail. Got it? Then
Yes, sir.
their resultant is given by the closing side of the triangle taken in order or reverse order. Here you see reverse order. It means taking in order was joining head to tail. Taking in reverse order means joining tail to tail and head to head. That is said reverse order. So tail to tail, head to head. This indicates the resultant of the two vectors. Now let me read out the statement, part by part, and I'll justify why such a lengthy statement was required. If two vectors represent two sides of a triangle up to this point, so A and B should look like two sides of a triangle. So the first part of the statement is necessary, right? And how should they represent the two sides of the triangle? If they represent only the magnitude but not the direction, will that be sufficient? Will that be sufficient? No. If they represent only the direction but not the magnitude, then will that be sufficient? Then also it is an incomplete information. So how should they represent two sides of the triangle? Both magnitude and direction. Fair enough. That is the requirement of this part of the sentence, both in magnitude and in direction. Then the resultant is given by the closing side of the triangle. If I just stop the statement here, then there is an ambiguity. How is the resultant represented by the closing side? Only magnitude? May not be. Only direction? May not be. So I have to remove that down. Therefore, I say closing side of the triangle. How? Both magnitude and direction. Then how should I close the side? Because I could have drawn an arrow here also, right? This is also closing side. So in order to remove that ambiguity, we say taken in the reverse order. So every part of the statement is important. What students end up doing is, sir, this statement is very lengthy. I have come across a study material where the entire triangle law is just given in one line. Can I use that? You can use that, but half of the information will be missing. And the teacher will feel very unhappy about it. And instead of 2 upon 2, they'll give you a 0 there. Because even if you miss one line there, if you write everything, and if you miss out on this one, taken in the reverse order, if you miss out on this, if you write only up to this, is it like actually giving you the idea of triangle of addition of vectors? You have two sides, but you don't know how to draw the third side. In the same order or in the reverse order, you are not. Therefore, every part of the definition is important. So this definition, write it as it is. Different types of vectors and all that, you can write that later on. But at least this definition, because we are going to take up a few examples of triangle of addition.
So different laws give different answers.
Pardon?
So different laws give different answers.
We will see that. We'll cross-check that. Right? Let us leave it as curious as of now. and we will literally use different laws and see if we are getting different results. What is your guess? Will different laws give us different answers?
Sir, yes. When I checked the previous.
Like suppose there is a group of scientists studying a rocket launch, right? Half of the scientists use parallelogram law of addition of vectors to calculate something, and the rest half, they use triangle law. If both end up getting a different result, then any one of them has to be wrong definitely, because both cannot be right simultaneously. So what does that bring us to a conclusion to? Triangle of addition of vectors should give the same result as parallelogram. Otherwise, if they are giving different results, what you see in front of your eyes is only one object moving. One object cannot be moving in two different directions because there are two people solving the problem. So only one of them has to be correct. It means basically triangle law, parallelogram law, polygon law, all of them give the same answer. And we are going to prove that. Once you finish writing, just use that hand raise symbol and I'll come. Now, one question just out of curiosity. How many of you know Hindi? Just raise your hands. If you know Hindi, a little bit. Okay, Ayush knows that. Prithvi Raj knows it. Rehan knows it. Nevin doesn't. Acha, Nevin also knows Hindi. Arey wow, Abdul Salam ko bhi aati hai. Okay, so one person doesn't know Hindi, rest of you know Hindi. That's okay, that's okay. Happens. It's not that I will continue the class in Hindi, that's not the idea. Sometimes I get emotional and I recall some very famous dialogues and all that. I get emotional and I use that in the class. That's the reason why I was asking. Nothing beyond that. The class will be in English. You don't have to worry. Otherwise, I can manage a class, full 1 hour or 3 hours class, completely either in Hindi or in English or in another language. I know 3 languages for sure. So if you want to ask me doubt, you can feel free to ask me either in Hindi or in English. That's okay. Right. So triangle of addition of vectors. Everyone has done this, written. Now let us take a few examples and solve it for yourself and see. Take one vector like this, another vector like this. Try to add it using triangle law. Or take one vector like this, vertically down, another vector horizontal. Try to add it using triangle law. Then take one vector like this and one vector like this. Is it even possible to solve it using triangle law? You won't be able to complete it, right? Then that is like being unfair to the law itself. So the thumb rule is that if you are planning to use triangle law, then at least the 2 sides should give you a chance of completing a triangle. So don't take those kind of things which land you into a trouble. At least take vectors like this. So this is the first vector. You keep it like this. The second vector is taken in an order. It means joining tail to head like this. Then the closing side of the triangle taken in the opposite order gives you the resultant from the tail to tail and to head. This is the result. So now we can write down the vectors. This is vector A, this is vector B, and this is your resultant, that is A plus B. Similarly here, let us say this is vector A and this is vector B. The resultant is given by the closing side of the triangle taken in the opposite order, like this. So this is vector A, this is vector B, and this is the resultant of A plus B. Like that, you can choose any example. As long as it gives you the facility of completing a triangle, that is safe. Done? Shall we move on to the next one? Now, in life, you may have to add sometimes more than two vectors. I'll give you one example. Suppose there is a body of mass 10 kilograms, and to this body, Ayush is pulling in the right-hand side direction. Rihan is pulling in the upward direction. And Nevin is pulling in this direction. And Abdul Salam is pulling in this direction. I could include the fourth, Prithvi Raj also is pulling in another direction. I could include the girl's name also, but she changed her name in between. Now I am in a dilemma as to which name is to be used.
It was actually my mom's name before, so I changed.
So what do I call you now?
Sidra. My name is Sidra.
Sidra, okay. And Sidra wants to pull it in this direction. In which direction will the body eventually go? Don't even try to answer that, because I didn't even give you the numbers, right? But if the question is, in which direction will the body go, can you choose to select only two vectors and jump to a conclusion based on that? That will be unfair, right? When there are 1, 2, 3, 4, 5 forces acting on it, how can you choose only two out of them? Even if you say, suppose if someone asks, there are so many forces acting on the body, why did you choose only two forces? If you say, no, sir, we are using only two forces because we learned only triangle law of addition of vectors and we know how to add only two vectors, therefore I'm taking two forces. Would that even be a reasonable argument? No, right? When there are 5 forces acting on the body, you should be able to take all the 5 forces into consideration. Will triangle law help you do that? Kind of, yes, but imagine how difficult it will be. Let us check that now itself. I will take this as the first vector and take this as the second vector. Or let me bring it a little bit here. These are the two vectors taken in an order. Then the resultant is given by the closing side of the triangle. This is the resultant of these two vectors. So now let me remove this and bring this vector back. This is the resultant of the first two vectors. Now I have to add this to the next vector. So what I do is I'll bring this next vector here, bring this vector here, and I have to add it taken in an order. Then the resultant is given by the closing side of the triangle taken in the opposite order, tail to tail, head to head. So now these vectors are also added. So now this is the remaining vector. Now to this vector, I have to add this vector. Like this, if I have to one by one solve all that, isn't that a very tedious thing? Can it be done? Yes. But is it a sensible way of doing this? It is looking more like a donkey work. Every time find out the resultant, then add it to the next one. Again find the resultant, again add it to the next one. That is a donkey kind of a work. Is there a better way of doing that? Yes. And that is your polygon law of addition of vectors. It means if there are more than two vectors to add, then it is very simple. Suppose this is one vector, this is one vector, and this is another vector, this is another vector, and this is another vector. Or let us say this is another vector. Suppose you want to add these vectors. All that you have to do is take the first vector, then take the second vector taken in an order, so tail to head. Then take the third vector taken in an order, tail to head. Then take the fourth vector taken in an order, tail to head. Then take the fifth vector taken in an order. Now, the resultant is given by the closing side of the polygon taken in the opposite order, tail to tail, head to head. This is the result. Isn't this wonderful? Otherwise, you'll have to use triangle law for every pair of vectors, get the resultant, then add it to the next one, again get the resultant, again add it to the next one. Instead of doing all that, this is vector A bar, this is B bar, this is C bar, this is D bar, this is E bar, and this resultant is resultant of addition of all these vectors. This is polygon law of addition of vectors. So basically speaking, polygon law is just an extension of triangle. In triangle law, you add only two vectors, keep on repeating the process, and that becomes a polygon law of addition of vectors. Is the idea clear? So write down the statement and take any bunch of vectors of your choice and draw the diagram. If you don't want to be very innovative, you can take the same diagram that I have drawn. Or if you want to be innovative, you can take whatever vectors you want. But at least take more than two, because if it is two vectors, it is only a triangle. So 3 is also okay, 4 is also okay. And since it is only the second class, it might take a while for you to get used to my style of teaching. If I'm speaking too fast for you to understand, then please do let me know. Okay, because online class dynamics, they are always different from offline class dynamics. I don't know since how many years you have been attending online. You might have attended, I suspect you might have attended at least 2 years of online. That should have happened, right? Unwillingly or, with a lot of discomfort and all that, but yes. But for me, this is not my first online class. I have started online classes 9 years ago, not because of COVID. Long time back. Right? So it is okay for me, but if you are finding any difficulty, then please let me know. I'll slow it down a little bit. If I'm going too slow, then please let me know. I'll speed it up a little bit also. If everything is okay, फिर तो ठीक है. Done? Polygon law of addition of vectors. Okay. Then comes the parallelogram law of addition of vectors. Something that we did yesterday. Parallelogram law of addition of vectors. If two vectors represent adjacent sides of a parallelogram, both in magnitude and direction, then the resultant is given both in magnitude and direction by the diagonal of the parallelogram drawn from the same point. Is there any phrase that is missing in this definition, which was there in the earlier two definitions?
In which order it must be taken?
There is no mention of order here. Did you notice that? So when you are adding when you are adding two vectors using parallelogram law, you should not join tail to head. You should join tail to tail only. Let us take two vectors here. This is one vector. This is another vector. Now let us join them using triangle law first. So I'll take this vector here. I'll take this vector here. And I'll draw the closing side of the triangle taken in an opposite order. Tail to tail, head to head. Is this parallelogram law? No, right? This is triangle. Let us keep this here. Now, I'll take the same two vectors. Same two vectors. Notice that I'm not touching this black vector. Black vector was the resultant in the first case when we had used triangle. Okay. So we will call this first vector as R1, resultant obtained using triangle law. Now let us try to add it using parallelogram. So we'll take one vector here, another vector here. Then we draw a line parallel over. It has to touch the tail exactly. Right. Then we draw a line parallel to the first vector. We draw a line parallel to the second vector. And then where these two lines meet, this point, from the common point where we have drawn the vectors, we draw a resultant that is up to the point of intersection of the two parallels. This is the resultant using parallelogram law, that is the second case. Earlier, Abdul had asked a doubt that, sir, whether we use triangle law or whether we use parallelogram law, or for that matter, any law of addition of vectors, will the resultant be same? You can check it for yourself. Isn't the resultant same? Exactly. Right? So this point is proved now. Whether you use triangle law or whether you use parallelogram law, the answer will always be the same. Got it? Understood? So you write down the statement, draw any one example, and write a note also there. Note, when two vectors are added using any of those laws, the resultant is the same. Think of it as a boat river flow. This one. So here you see that this indicates small water waves. Right? That is my idea of water waves, because it's very difficult to make a simulation with exact water waves. And I'm not designing a game here in any case. So you can see that those are water waves, a small representation of that. This is our humble looking boat. And the boat is trying to cross the river from point A to point B. But because of the velocity of the water, it will not be able to reach point B. It will get dragged down. And you can see that, click. And it crosses the river, but reaches point C. Now, here you can solve this problem by looking at the velocity of the boat in the upward direction, the velocity of the water in the horizontal direction, and therefore, when you add them, you get the resultant velocity of the boat. Can anyone tell me which law has been used in order to show this representation here? Triangle law of addition, right? It is so innocently looking like a triangle, isn't it? But can it be solved using parallelogram law? Yes, it can definitely be solved using parallelogram law also. You see, I draw a line parallel to this one, parallel to A from this point, B, like this. I draw a line parallel to B from here. Oh, wait, why should I do it? Can you prove it for yourself that even using parallelogram law, you'll get the same answer? For parallelogram law, first of all, you should not leave the vectors here itself. This is the velocity of water, right? So what you do is, you bring it here. And this is the velocity of the boat. I'm just drawing right on top of that so that we get the lengths accurate. This is the velocity of the boat. Join tail to tail. That is how you should start your parallelogram law of addition of vectors. Now draw a line parallel from the tip of B parallel to A, and draw a line from the tip of A parallel to B, and now draw the resultant. Isn't this resultant what we have drawn just now? This one, same as this one. So one is using triangle law, one is using parallelogram. You see, you get the same answer. And how can you see the displacements? You see the displacement. Now carefully observe, as the boat is moving, the magnitude of the vectors will also increase. You see this grayish colored vectors, how their magnitude is increasing. I'll show that to you once again. Let me remove the velocity of the boat, velocity of water, and resultant velocity. Now we'll see only the displacement magnitudes. You can see that, how the vectors are increasing, because the length of the vector is supposed to indicate the magnitude. Therefore, as the boat is moving, it is covering more and more displacement, and therefore the size of the vectors increases. And what happens if you tilt the boat? If you tilt the boat a little bit, you see, you can make the boat, now you can see the boat's velocity, water velocity, and the resultant velocity. You can tilt the boat, so you can adjust the boat angle to such an extent so that once you let the boat move, it will move exactly parallel to the dotted line. It means it will be able to cross the river along the shortest path. Now tell me, doesn't the study of all this require vectors? Can we even try to solve this kind of problems unless you have the knowledge of vectors? That is the reason why addition of vectors, subtraction of vectors, and then later on a technique called finding out component of vectors, all that is very useful. Tomorrow, we will look at a quantitative measure of parallelogram law of addition of vectors. Then we'll go to another topic called resolution of vectors. Okay? That's all for today. Have a nice day. Bye.